Listen to this first sound. And now listen to this second sound. Which one sounds higher? The first one, right? But that's really weird. The first sound was a tone of 440 Hertz. The second sound was comprised of a bunch of tones, all of which were 500 Hertz or above. And yet, the second sound sounds lower than the first. That's really strange. We normally think of pitch as being determined by the frequency of a sound. So listen to this. It's a frequency of 220 Hertz. We're going to follow that with a frequency of 330 Hertz. So that frequency is higher than the first one. But look what happens when we put the two together. The resultant pitch that we perceive is actually lower than either of them. This phenomenon is called the missing fundamental. Is it because our brain's playing tricks on us, or is something else going on? Well, in order to explore this, we're going to have to use a little bit of maths to find out. So you're probably familiar that sound is a kind of wave, and in this room, the way it works is that something that generates a perturbation and creates some anomaly in air pressure will move across the room, and we will perceive that as sound. One perturbation might be where we're going to use a violin, and if we draw a violin bow across the string vibrates like this, and what happens is that the air around that then gets perturbed, and the sound pressure waves reaching us appear as sound, and that's what we hear. Those four different strings, those four notes, are not just pure tones. They're actually a combination of frequencies. When a violin string is excited, it vibrates at the fundamental frequency. The fundamental frequency of the note is usually what our brains register as the pitch of that note. And it's also usually the loudest. But as we'll see, it isn't quite that simple. So even though the second string on the violin is tuned to an A, which has a frequency of 440 Hertz, if we analyse the composition of the sound actually generated, we can see it also vibrates at multiples of the fundamental frequency, at twice the frequency, 3 times the frequency. These things are called harmonics. So what we hear is a combination of a load of different frequencies excited just by one bow scraping across the string. And if we play the same note on the trumpet, it's at 440 Hertz, but we can see that it has a very different spectrum of different harmonics. So the multiples of 440 are the same, but the relative strength of each is different. And this is one of the significant factors that determines the tone quality of one instrument versus another. In other words, why different instruments sound different. So what's this got to do with the missing fundamental that we alluded to earlier? Well, we're going to create a set of digitally formed pure sine waves of frequencies 110, 220, 330, 440, 550 and 660 Hertz. What we find is that the more multiples of the 110 that we add, the tone quality changes, but the pitch that we hear, 110, does not. So now let's listen to what happens when we remove the fundamental frequency of 110 Hertz. We still hear it. This is the phenomenon of the missing fundamental. We can explain this if we look at what actually happens when we add these waves together. The resulting sound wave is a lot messier, but it still has a regular repeating pattern, and the period, which is the shortest repeating section, is exactly the same as the fundamental. This is what determines what we perceive as pitch. Well, let's look at the resultant waveform, having removed the fundamental frequency. What you'll see is that the shortest repeated section still has the same period as that of the fundamental frequency. And therefore, even though we've removed it from the contribution of the tones forming that sound, we still hear it, because when you combine all of the others, it is still there. So this tells us something really interesting about how we perceive pitch. So let's consider a set of tones 220, 440, 660 Hertz. When we combine all of those, the pitch that we perceive is the lowest of these, 220 Hertz. The 440, 660 are multiples of the fundamental, and they are therefore harmonics. But something really weird happens if you add yet a higher frequency of 770 Hertz. 770 Hertz, adding this, results us in perceiving a pitch that is lower than anything of those waves. It's 110 Hertz that we are perceiving as a new pitch. So this isn't a case of our brains playing tricks with us. By adding a frequency of 770 Hertz, we have changed the waveform, and the pitch of that waveform corresponds to that of 110 Hertz. Thanks for watching this video. If you really liked it, then please do subscribe to our RI YouTube channel. And if you'd like to support us, then please do so via Patreon. Thank you.